Today we'll talk about cyclotomic extensions. Okay, so what are these? Well, they are what we usually call the roots of unity. So let me make this more precise. So let's take a number n greater than or equal to 1, and let's take the polynomial f of x to be x to the n minus 1. Okay, and my base field here is the field of rational numbers, and what we're going to do is to look at the splitting field of this. So let k or maybe I'll call it k sub n in this case. So okay, let's fix n for now. So let me just call it k. K is the splitting field of this polynomial fx over q. Okay, and recall what does that mean. You just have to adjoin to k the roots of this polynomial over some algebraic closure. So since the complex numbers is one ready algebraic closure that we know about, so all we have to do is adjoin the roots of unity, the roots of this polynomial, which if you remember are just 1 zeta square till zeta to the n minus 1, where what zeta is just e to the 2 pi I by n. Okay, and recall we have our usual picture on the unit circle. So one of the roots is 1, the next fellow is zeta, which forms an angle of 2 pi by n, and then the next one is zeta square. So they form the vertices of a regular n-gon on the circle like this. Okay, so those are the roots of unity, and this field k is what we call the cyclotomic field or the cyclotomic extension of q, and this is indexed by this number n that we fixed. Okay, so here are some basic facts about this. So let's look at this cyclotomic extension k. So we encountered this once before, one of the examples, that well, you don't need to adjoin n minus 1 or n of these roots. It's enough to adjoin just one of them, and that's because once you adjoin zeta, all the powers of zeta are automatically in this field. Okay, so that's k is just q zeta. Now fact number 2 is that q zeta is a Galois extension of q. Okay, so this is a Galois extension. Well, why is that? We need to check two things: that it is normal and separable. It's normal as an extension because it is the splitting field of a bunch of polynomials. Well, in this case it is the splitting field, since this is given as a splitting field of some polynomial. And separable comes for free because observe that we are talking about characteristic zero fields, and there we have seen that all algebraic extensions are automatically separable. So this is just, both are straightforward in this case. So what we are talking about is a certain Galois extension of the field of rational numbers. Okay, and our goal is really the following theorem, proposition, which says that the degree of this Galois extension is phi of n. So what is phi of n? This is Euler's totient function, which counts. So this is the number of natural numbers or number of integers k from 1 to n that are relatively prime to n, Okay, so you've seen this before. So for example, if I take phi of 6, this is just 2 because among the numbers 1, 2, 3, 4, 5 and 6, only 2 of them are relatively prime to 6, which is the numbers 1 and 5. Okay, now let's prove this theorem. That's our goal. So various facts to observe. So here's observe the following. So I'm going to prove this over the course of several steps. Let's make some preliminary observations. the roots of unity that I just wrote out, 1 zeta zeta square. So let's call that gamma n. So these are what we call the nth roots of unity. So these form, well, they form a multiplicative group, right? So this is a think of it as a subset of the multiplicative group of non-zero complex numbers. So this forms in fact a cyclic group. Okay, gamma n is a cyclic group, and of course it has zeta itself is a generator, but there are many other generators for this group gamma n. So which are the generators? How, which elements generate this group? So let's say gamma equals zeta power k, okay, generates, so let me generates this cyclic group means what? Well, recall, when does an element zeta power k generate the cyclic group? Well, this can only happen if k and n are relatively prime. Okay, so this is just from our usual knowledge about cyclic groups and so on. And so what does that mean? It says that in fact there are exactly phi of n generators for this cyclic group. Okay, so therefore there exists phi of n generators for this cyclic group gamma. So there are those many possibilities, and these generators are what are called the primitive. So let me give this a name. So gamma n star is just a set of these generators, or it's the set of all zeta power k, k from 1 to n, such that the GCD of k with n is 1. Okay, so this set is called the set of primitive nth roots of unity. And in our previous example, so when I talked about n equals 6, for instance, so these are the so I have sixth roots of unity. So these are the 6 of them. Okay, and so this is zeta is e to the 2 pi I over 6, and then the various powers of zeta, and only 2 of them are primitive. So which is e to the 2 pi I over 6 and e to the 5 pi I over 6. 2 pi I into 5 by 6. Okay, so these are the two. So this is zeta power 5. So these are the two primitive 6th roots of unity. The other roots of unity are not primitive. Okay, now let's also look at what can we say about the other roots. So this is, so observe more facts. So maybe we'll number these. So observe fact 1, observe fact 2, that if d divides n, then what does it mean? It says that the dth roots of unity are necessarily contained inside the nth roots of unity. Okay, so why is this? Well, it's sort of more or less obvious. You just have to see, take any dth root of unity and just see that it lives inside the set of nth roots of unity, right? So let's just check this, quick check. So if gamma is an element of gamma d, that just means gamma power d is 1. Of course, d divides n, therefore gamma d power, if I raise this to the n over d, then that's just gamma n, and 1 power n over d is just 1. Okay, so if something power d is 1, something power n is automatically 1. And in fact, the converse is also easy to see, that if n divides, if gamma d subset of gamma n, so another quick statement for you to check, if this is contained, then d must divide n. Okay, so I leave this as an exercise. Now let's look at the various elements of order d dividing n. So why did I talk about d dividing n? So observe, if I take gamma n, the elements, so what can I say about a typical element of gamma n? An element of gamma n has order Okay, I am talking about the cyclic group gamma n. In that cyclic group, this element must have some order, and recall that the order of an element necessarily divides the cardinality of the group, right? So I can therefore decompose gamma as follows. I say, okay, let me take, I'll write it as a union. Okay, and this union is disjoint. It's a union over all d dividing n. So d is now a number between 1 and n of the set of elements gamma in gamma n, such that the order of gamma is d. Okay, so I can write gamma n like this as a disjoint union. So if you go back to this example, notice that the two things I circled in red both have order 6. Okay, so these are the primitive roots of unity, they are the generators, so these two have order 6. Now if I take this element here, which is the element 1, this has order 1 because it's the identity. Okay. Now if I take the element at the other end, that's minus 1, this has order 2, because when I square it I get identity, and the remaining elements have order 3. So if I take this element and this element, they both have order 3 in the cyclic group. Okay. And the original elements, like I said, both have order 6, so these are order 6. Okay, so this is the decomposition I am talking about. Just look at what the orders of the different elements are and split them up into a disjoint, split gamma n up into a disjoint union of subsets of different orders. Okay, and now here's the very interesting and important fact. If I look at these elements here, the ones whose order is exactly d, then you will observe that this is actually just the set gamma d star. Okay, so in other words, this is the union d dividing n of gamma d star. Okay, now maybe again I leave this as a little exercise for you to check. It's a easy sort of exercise. So look back on this previous diagram that we drew and sort of see how those came about. So notice that the elements of order 3 that I drew in this picture are exactly what we would usually call omega and omega square, the cube roots of unity, and so on. Okay, and the proof is just more or less from the definition. Just see what it means for an element to have order d and what it means for an element to belong to gamma d star, and you will notice that these two are exactly the same. Okay, so in particular, what does this prove? So this is a sort of an aside. Observe that the cardinalities on both sides must be equal. Right. So this in fact implies that n, which is the cardinality on the left hand side, is the sum of phi d dividing n. And this is one of those classic identities for the Euler-Torsion function. Okay, but our main interest is in trying to understand this cyclotomic extension. So let me so we quoted facts 1 and 2. Let's move on to fact 3. Which is really a definition. So let's define the polynomial of interest, which is phi n of x, and this is just the product of x minus gamma, where gamma ranges over the primitive nth roots of unity. Okay, and observe that, well, at the moment, what can I say? I can say that I'm only taking the primitive nth roots of unity. This is maybe a polynomial with complex coefficients. That's about it so far. I know something more about it. It's a monic polynomial, and the degree of this polynomial is exactly the number of terms, which is the cardinality of gamma n star, okay, which is phi n. Okay, so this capital phi n of x is what's called the nth cyclotomic polynomial. It's got roots. The roots of this polynomial are just the primitive nth roots of unity. Okay, so observe that the decomposition I talked about earlier gamma n being a disjoint union of the gamma d stars, it translates into the following identity. T dividing n. It's the same thing. You're just taking those all n roots on the left side, and you're sort of taking roots collected together by their order on the right hand side. So this is an important identity because it actually allows you to calculate what the phi d's are. Okay, so observe, this can be used to recursively compute these polynomials capital phi n's by, well, for example, so let's just do the first few cases. So if I take n equals 1, then it says x minus 1 is just my polynomial phi 1 of x. X square minus 1 is phi 1. So I'll just suppress the x on the right side, phi 1 into phi 2. So what does this mean? It tells me that my polynomial phi 2 is just x square minus 1 by x minus 1. Okay, so similarly x cube minus 1 becomes, so observe, I should only run over the divisors of n. So it tells me phi 3 is just x cube minus 1 by x minus 1. So that's x square plus x plus 1. Okay, and so on. So for example, if you did phi 6, you'll notice this will be, if you wanted to do it for phi 6, this is x to the 6 minus 1 equals phi 1, 2, 3 and 6, and from here you could just take x to the 6 minus 1 and divide it out by the preceding 3 fellows. That answer is phi 6, whatever it turns out to be. Okay. Now one obvious conclusion from here, really, this recursive procedure is that even though it seemed to have complex coefficients a priori to start with, in fact it has rational coefficients. Why? Well, because we can sort of compute it in this way. Okay, we can calculate it by this recursive procedure. So observe, this procedure implies the following, that phi n of x, phi n of x is actually polynomial with rational coefficients. Why is that? By, if you wish, by the division algorithm. Okay, so what do we mean by that? So let's maybe prove this formally. So what I mean is, it's an inductive proof. Proof is by induction on n. Okay, so these formulas here sort of prove it for the first few values of n. So let's just say we know how to prove it for n. So true for n equals 1, and suppose it holds for all n less than or equal to some capital N minus 1. Then how do you prove it for capital N? Well, you just use the recursive procedure. You will write it as phi 1, whatever. I don't know what the divisors are, so maybe I'll just write it in general. Product of phi d of x, t divides n, and from this I'll just pull out the last term phi n alone. So I'll take product of the phi d's, d dividing n, but d is strictly smaller than n, times capital phi n of x. Okay. Now by induction, this product, so I've assumed already that all the phi d's for d smaller than n are in qx, right? So this is in qx. Okay, so what does that mean? That at least I know the following, that this is in qx, right? In fact, it's in z of x. Now when I divide this, and I know that phi n of x is just the quotient of these two polynomials, right? So I know that this polynomial here, whatever we should call it something, f of x. So I know this f of x definitely divides x to the n minus 1 in c of x, right? If you view everything as being polynomials with coefficients in complex numbers, then f definitely divides the polynomial x to the n minus 1, and the quotient is exactly what we are calling phi n of x. But how does one compute the quotient? So if you sort of remember what the division algorithm does, you sort of calculate the coefficient, or if you wish, if you think in terms of long division, how do you perform long division? So you take x to the n minus 1, and then I have this polynomial f of x here. So I sort of divide, I take the coefficients of x, maybe some a k x power k. So maybe this is monic plus something a1 x to the k minus 1 and so on, and I sort of divide out coefficient by coefficient, right? So if you just imagine how the long division process is carried out, so you'll notice that this will be some x to the n minus k plus some next term, but this next term will only involve rational numbers. Okay, why is that? Because if you remember how those are computed, it only involves these numbers a1 or the numbers which arise during this process, all of which are rational. Okay, so that's sort of one argument. So you can make this argument a bit more formal as well, but the broad idea is that if fx divides this in cx, and if these two are in qx, and if f and since these are in qx, one can also conclude that f divides x to the n minus 1 in qx. In other words, the quotient is actually in qx. Okay, so what does that mean? Therefore, we have concluded that phi n of x has rational coefficients. Okay, so that's an important simplification. But in fact, there is something more, and this is rather remarkable. So there's a little proposition here that actually these polynomials have integer coefficients. Okay, not just rationals. In fact, their coefficients are integers. Okay, so to prove this, so you had seen something along these lines in the earlier lecture on Gauss's lemma and so on. So to use this, to prove this, we use a corollary of Gauss's lemma. Okay, so we use, let me state this as a lemma, because it will be used repeatedly in this whole analysis of cyclotomic polynomials and so on. So this lemma says that if I have f, g, h polynomials with rational coefficients such that f equals g into h, okay, let this happen. Now if monic, so I should also set qx such that they are all monic polynomials, and fgh monic, okay. Now if f is in zx, if f has integer coefficients, then both g and h also have integer coefficients. Okay. So this was one of the corollaries that you had looked at. The following corollary to Gauss's lemma. So please look back on the lecture on Gauss's lemma. This just involves observing that the contents are 1 on both sides and then applying Gauss's lemma. Okay, so this is a very, very important statement, that if I have two monic polynomials g and h whose product is f, and if f is integral, it has integer coefficients, then g and h must also have integer coefficients. Okay, now how does that help us in this case of phi n? Well, again, this is by induction. So let's complete the proof of this proposition. Proof of this proposition. We don't even really need induction here. So observe that x to the n minus 1 has been written as the product of phi n, or just say, okay, let me go back to my earlier inductive sort of thing, phi n of x into f of x. Okay, and what is f of x? It was the product of the other d divides n, d is smaller than n. Okay, So now we'll prove this proposition also by induction if you wish. So it's true for n equals 1. It's true that phi 1 of x has integer coefficients. And again you assume it's true, assume for n less than n minus 1. Then you try to prove it for capital N itself. Okay, and now that's this identity here, x to the n minus 1 is phi n of x fx. Now just apply the lemma. Okay, so by the induction hypothesis, so since we have assumed it for all n, so for all n, so then by the induction hypothesis we conclude that each phi d of x, so each phi d has integer coefficients, okay, and it's all monic. So we know that the phi d's are all monic. So therefore their product is also integral and monic. Okay, so that we know, but so what else do we know? We know it's all rational. So let's just look at so in this case I guess we didn't quite need the induction hypothesis. We just need to know that they are all rational. So we just need to know that they are in Qx. So okay, sorry, we don't need this really. So let's just recall from what we already know that fx is, so we don't even need an induction here because we're just going to use the lemma straight away. So I already know that this is in Qx. We have already proved that portion of the statement, and now so apply the lemma that I just talked about. Okay, the lemma says that if I can write f as gh where all three are monic, okay, and that's exactly what I can do here, right? So I already know this is monic. Okay, so x to the n minus 1 is monic, phi n is monic, fx is monic, right? The fact that it is monic is just from the definition. All of them are in Qx. Okay, that's the bit I just proved by induction, and so by the lemma it means that okay, but since the left hand side x to the n minus 1 is integral, it's got integer coefficients, therefore phi n of x and f of x both have integer coefficients. Okay, but I'm only interested in phi n if you wish. So that completes the proof. Okay, just a simple application of Gauss's lemma.